Greetings, everybody. Learning is a hobby here. I wanted to go over I mentioned this over the weekend, but I wanted to get back to some math videos. So I wanted to go over section 1.5 in Simmons. In this video, I'll be doing the summary of excuse me. I'll be doing the summary of the section, and then in the next video, I'll do the exercises. I actually haven't had a chance to start on the exercises yet, so that won't be done today. But sometime in the next couple days, I'll post a video for the exercises. All right, so let's just jump right into it. Let me bring up my notes for the section. Okay, so here are my notes. Section 1.5 is on free fall, and he does an example on free fall, and he does an example on the motion of a pendulum. So we've already talked about free fall under gravity with no other forces acting on the body. So vertical motion, straight line motion. The differential equation that governs that type of physical system is this one. Second derivative of position is equal to constant acceleration, which is the acceleration due to gravity. Here we're assuming that the going down is the positive direction, because notice I'm counting g as a positive number here. All right, and then if we assume that the initial velocity is this number v0 and the initial height of the object is y0, then we can go about solving the differential equation. So you just anti-differentiate. The first derivative, or the velocity, is gt plus some arbitrary constant. And if you plug in 0 in for t, you get that c1 is equal to v0. So in other words, the initial velocity. So the velocity looks like this: gt plus v0, and then anti-differentiate with respect to t one more time. And you get the position function, y equals g over 2t squared plus v0 t plus an arbitrary constant. And again, if you plug in 0 in for t there using the initial condition, you get that c2 is the initial height, y0, and this is the equation. Okay, so that's the position equation. And this one here is the velocity equation for the situation. All right, then he goes into deriving this formula here. If y0, if the initial velocity and the initial position are both 0, then the equations simplify to these two here. V is gt and y is g over 2t squared. And using these two equations, you can eliminate the parameter t, and that gives you the velocity in terms of the distance fallen. So that gives you this formula here. V is the square root of 2gy. All right, and then he says we can derive the same formula. So I don't know why my nose is running. We can get the same results using the principle of conservation of energy, which says that kinetic energy plus potential energy is constant. And using the initial conditions here, v of 0 is 0, y of 0 is 0, implies that c is 0. If you plug t equals 0 into the equation here, you find that c is 0. So that means that the kinetic energy is equal to the potential energy, or in other words, 1/2 mv squared equals mgy. And if you solve for v in that in this equation here, you get the same thing. V is square root 2gy. All right. Falling with linear resistance, air resistance. So here, instead of just the object falling under the acceleration due to just under gravity, the force due to gravity, now we're also introducing a linear air resistance force. So in other words, we're going to assume that the air resistance is directly proportional to the velocity of the falling body. All right, so in that case, you get this differential equation. This is a linear second order non-homogeneous ordinary differential equation. You can solve this by reducing the order. The second derivative of position is the first derivative of velocity, and the first derivative of position is just the velocity. So you actually get a first order ODE here, which you can solve by separating variables, unsurprisingly. And then you just solve that, you find your antiderivatives and so on. And when you go through the process of solving everything, then you get this equation here for the velocity. So the velocity is g over c times 1 minus e to the negative ct. And then if you want to, you can, excuse me, you can replace v with dy dt, and then you could go on further, just solve that first order differential equation, and you can get the position, the equation for the position at time t as well. He doesn't actually do this part. He just says you can do it, but I went ahead and did it so you can see what the position equation looks like. All right, so there's some interesting properties here of these equations. Notice that as t goes to infinity, the velocity approaches a limiting value. The limiting value is g over c, which is known as the terminal velocity. So past a certain time, the acceleration, as the body is accelerating, the the air resistance at some point balances that, and you get a constant velocity. You get a constant velocity eventually, in the long term. So that's called a terminal velocity. That you can also see that this shows up here in the position equation. Over in the long term, notice that the position changes linearly rather than with this extra exponential factor here, which means that eventually the velocity approaches a constant value or a limiting value. All right, so here, that's all I'm saying here, terminal velocity. If you take the limit as t goes to infinity of v, notice that the limit here goes to g over c. That's the terminal velocity. All right, then the next example he goes over is the motion of a pendulum. This was quite an involved problem here, but we'll go through it step by step. So here you have a pendulum that has a length a. So you have a mass hanging from this rod here of mass m, and you lift it up to, if this is the vertical position here, you lift it up, the mass m, up to an angle of alpha, which I have here, and then you drop it, and it starts to swing back and forth. I'm sure you guys are familiar with pendulums. And we want to describe that motion. So here, in order to do that, again, we use conservation of energy. So 1/2 mv squared equals mgy, for the same reason above in the previous problem. So we replace v with a d theta dt, because if you look at the picture, if this is the arc length, then s is a theta. If this is the angle theta here, and this is the angle alpha, s is a theta. That's the formula, as long as theta is measured in radians. And you can differentiate this with respect to time. So ds dt is a d theta dt. Replace the velocity with that in this equation. You get this here, and then y is actually, this might not be clear as to why this is, but let me actually draw some lines here so you can see why that's the y value. All right, in time t, the mass has, because it's swinging this way, right? The mass has traveled this distance y, and that distance y by trigonometry is this value here is a cosine alpha, and this distance here is a cosine theta, and the length here is this minus that, right? Which is what I have written here. All right, so just simplifying this equation here, notice you can divide out by m, and actually you can get rid of one of these a's here, and then multiply by 2, so just simplify the equation, right? And you get this one here. So d theta dt squared is 2g over a times cosine theta minus cosine alpha. Excuse me. Taking the square root, we get, well, actually you get plus or minus, but we take the negative one because the pendulum is swinging in the, the negative direction. So d theta dt is negative square root 2g over a times square root cosine theta minus cosine alpha. Okay, and then we can separate variables here, and when we anti-differentiate, we get that t is negative square root a over 2g times the integral d theta over square root cosine theta minus cosine alpha plus your arbitrary constant, right? And then we can actually say a bit more. This is the indefinite integral, but we can actually make this into a definite integral. Let's say that t is the period of the pendulum. The period of the pendulum is the time it takes for, let me use red for this. The period for the pendulum is the time it takes for the pendulum, whoops, why did it? For the pendulum to swing through one, I don't know what, go forward and then back to, its starting position, right? That's the period of the pendulum. Okay, so if we just look at, going from alpha to an angle of 0, that's 1/4 of the period. So t over 4 is equal to this integral here. We can get rid of the arbitrary constant because when theta is alpha and theta is alpha when t is 0, so that means that c has to be 0, right? Because if you go from alpha, the integral from alpha to alpha is 0, right? So you get this integral here with the limits of integration. So theta goes from alpha to 0, and then just to make the integral look have a lower bound of 0, when you swap, you just have to multiply by a negative sign, so you get double negatives here, which gives you a positive over here. All right, so you get this integral t when you multiply it by 4, t is equal to 4 times this expression here. And then we can, what we're going to do, what he does is he wants to manipulate this integral to be in a specific form so that we can, well, let's go through it and you'll see why. All right, so using these two identities, cosine theta is 1 minus 2 sine squared theta over 2. Cosine alpha is 1 minus 2 sine squared alpha over 2. And plugging that in into the integral here, we get this expression. So underneath the radical, when you simplify everything, you get 2 sine squared alpha over 2 minus 2 sine squared alpha theta over 2, and then you can factor out the square root of 2 in the denominator, multiply it by the square root of 2 in the denominator of the factor outside the integral, which gives you an extra factor of 2 in the denominator. 4 divided by 2 is 2, so that's where this 2 came from over here. All right, and the integral looks like this. And then we do some more manipulation over here. We let k equal sine alpha over 2, and that makes the integral look like this. And then choosing, again, we're doing this for a specific reason. It may seem kind of like arbitrary, but then letting the angle phi equal pi theta over 2 alpha. Then phi goes from 0 to pi over 2 when theta goes from 0 to alpha. And we make a substitution. So letting sine of theta over 2 equal cosine of sine of phi, then and then differentiating to find the differential, we get 1/2 cosine theta over 2 d theta equals k cosine phi d phi, and we need to solve for d d theta. So, dividing both sides by 1/2 cosine theta over 2 gives us this expression here. And then using the fact that cosine squared theta over 2 is 1 minus sine squared uh, theta over 2, which is the same thing as 1 minus k squared sine squared phi from the identity that we had here. Not the identity, sorry, from the substitution. And then same thing over here, k squared cosine squared phi is equal to k squared minus k squared sine squared phi. These two identities are just the Pythagorean identity, right? Hopefully that's clear. And then, again, using the identity that, the substitution, we get that that's equal to k squared minus sine squared phi over 2. And then, you can take the square roots and plug it in to this, to the differential here, and you get this expression. All right, that's kind of a lot to take in just by looking at it. So you might actually want to try that yourself, actually um, do the substitution yourself, just to make sure you understand where all the pieces came from. All right, plugging that in, we get this integral. T is equal to 4 square root a over g. And now the angle goes from 0 to pi over 2 rather than from 0 to alpha. The differential d theta, when you plug in, when you plug in the value that we found here for d theta, you get d phi over square root of 1 minus k squared sine squared phi. And this integral here this is why we wanted to do all this. This integral here is an elliptic integral of the first type, which is denoted like this: fk pi over 2. So it's a function of k, the value of k, and the angle here, the upper angle is pi over 2. So this is what an elliptic integral of the first type looks like. Okay, now the reason that we're writing it like that is because their elliptic integrals don't have closed form solutions in terms of elementary functions. There's numerical ways of finding values of the elliptic function, but there is no closed form solution to those integrals. Okay, so this is the exact value for the period here. All right. So that's why he wanted to go through all that, all those substitutions and everything, just to write it in terms of an elliptic integral. All right, going back to the original differential equation, we can do a small angle approximation to get an approximate solution that you can solve exactly. We actually did an example like this in Taylor, I forget what section it was, but there was like a problem where you had like a skateboard going down like a half pipe or something, and we used a similar technique for solving that differential equation. So here, going back to the original differential equation over here, what we can do is, instead of taking the square root and integrating, what we can do is differentiate again, and using implicit differentiation, the left-hand side differentiates to this expression here: 2 d theta dt times the second derivative of theta with respect to t equals 2g over a times negative sine theta d theta dt, because theta is a function of time, an implicitly defined function of time. Notice you can cancel the d theta dt's, assuming that it's not 0. So you get this second order ordinary differential equation. It's actually homogeneous. So here, d squared theta dt squared is equal to, this one over here, approximately, if you use a small angle approximation, negative g over alpha, negative g over a times theta. Remember, for small theta, sine theta is approximately equal to theta. That's called a small angle approximation. All right, so we get this linear first order differential equation as an approximation over here. And that we can solve the general solution looks like this. We've actually show that this is a solution in, I think, in like section 1.2, I think we did that in the exercises. So it looks something like this. Theta is C1 sine square root G over A T plus C2 cosine square root G over A T. And we can solve for the constants by using our initial values. So theta is alpha when t is 0. That when you plug that in, you get that C2 is alpha, and the initial velocity is 0. So when so if you plug that into the derivative, take the derivative of theta with respect to t, and then plug in, plug in t equals 0, you find that C1 is 0. So that we get the approximate solution here. Theta is a cosine square root G over AT, which is not surprising, right? The vertical motion of the pendulum oscillates, like a sine or a cosine curve, right? It goes, down, then back up, then down, then back up, then down, and back up, and so on, right? Right. So with that solution, that says that the pendulum approximately, since this is an approximate solution, has approximate period 2 pi times square root A over G. And if there's a nice little thing you can note that you might notice, if you use the exact solution, when you plug k equals 0, the elliptic integral simplifies considerably to this. So t is 4 times square root A over G times the integral from 0 to pi over 2 d phi. And the integral is just equal to pi over 2, right? And if you simplify this, you get the same period that we have over here, 2 pi square root A over G. And that's it. That's basically the summary of that, the summary of section 1.5. So like I said, let me just stop the screen share for a second. I haven't had a chance to do the exercises for this section yet, but I'll try to do that over the next couple days. I do have work, so I'll have to find some time in between things to work those problems out. So thanks for watching, everybody. Look forward to more math videos. I want to finish up, like I've mentioned several times already, I want to finish up chapter 1 in Simmons. I want to finish up chapter 1 in Schifrin, and then I'll get back to Spivak. All right, so do like and subscribe if you have not done that already. Please, it helps the channel grow. It helps YouTube know to recommend these videos to people that are like-minded to to you and me. And I'll see you guys in the next one. Until that time, keep learning, everybody, and let me know what you think in the comments. All right, I'll see you in the next video.